Hi everyone, it's Mr. DuBrow. I'm sorry I'm not at school today, but my son is sick, so I'm at home helping take care of him. But I wanted to make sure that you guys got the same as the other sections yesterday. And so I'm making a couple videos, and you can see in front of you what the schedule is for today. We're going to be talking today about electric potential energy and voltage. And so these are two concepts that are not going to be directly tested on Monday's test, but I feel that they're important enough to go over because they'll help you understand what you've learned so far. And they also kind of introduce what we're going to do next with circuits. So I'm going to make a couple videos. In the first video, I'm going to go over a couple questions from set 3. Specifically, I'm going to talk about 55 and 57, and then depending on time, I might also do 47. And then in the next video, I'm going to give a short lecture on electric potential energy and voltage. And so I ask that during both of these videos that you take notes. And you should be watching this as an entire class. Okay, and then for the rest of the time, you're going to play an experiment with a couple of PhET labs, and you're trying to figure out what is happening in each of them. And so you're going to write a 1-paragraph summary of what you see. And then when you finish that, you should work on set 4. Okay, so that's the outline. Let's go ahead and get started with the questions, okay? So we're going to start with 55. And so for 55, we have a situation where we have the surface of the Earth, and we're trying to levitate a proton and then later on an electron. And so what we know is that the force of gravity is going to be equal to the electric force. That's the only way that these forces can balance. So the electric force is equal to the force of gravity, and now we have to decide how are we going to write that force. And one way that you could write the electric force is K big Q little q over r squared, and the force of gravity is big G big M little m over r squared. But in this problem, we don't really know what big Q is. All we know is little q, the charge of the proton, and then little m, its mass. So we don't want to use this definition of force, we want to use a different one, which is that, well, we'll say it like this, that the gravitational field G is the ratio of the gravitational force divided by the mass, and the electric field E is the electric force divided by the charge. So that allows us to rewrite things. I'll just make this line a little bit shorter. So the electric force is actually Q times the electric field, and the gravitational force is M times G, the gravitational field. So hopefully you can see how things go together, that the electric field and gravitational field go together, and charge and mass kind of go together. And of course, forces go together. So this is the equation that we want to solve, and we're just going to solve that for E. So that's going to be mg over q. And I won't do the numbers right now, but you get the idea. And the important thing is that E points in the direction of the force, on a positive test charge. So what that means is that if I have a positive charge here, the electric field is pointing up because it points in the same direction as the force. Another way to look at this is that F is equal to QE. If Q is positive, then F and E have to point the same way. It's kind of like saying F equals MA. A and F point the same way because M is always positive. So that's part A. But now, what happens if we replace it with a negative charge? Okay, so same situation. We have a negative charge, and this time we draw the forces, and it should be no surprise that we have the exact same forces because it's still balancing, force of gravity and the electric force. And we go through the same calculation. So Q times E equals M times G. And we're going to get a slightly different number because the mass of the electron is different. So the number for the field won't be the same. But now which way does the field point? Well, if you think about F equals QE, electric force, well, the charge is negative. So what that means is that E also has to be negative in order to get a positive force. So electric charges, negative charges, actually have a field in the opposite direction. So the field would have to be this way. Let me say that again. Negative charges move opposite to the electric field. And so that's why if there's a force upwards on it, there has to be a field downwards. Okay, so that's 55. Now let's do 57. And 57 is actually a 3-dot problem, which is kind of mislabeled. Okay, and what we had in 57 was a coordinate axis, and we had 3 charges. Q1 was a positive charge up here. Q2 was a negative charge down here. And then Q3 was a negative charge down here. And we want to know what is the field at the origin. Okay, so there's our origin. We put down a tiny positive test charge, and we think about, well, how do we set this up? Well, this would be a lot easier if we had, for example, Q1, Q2, and our test charge right here, maybe plus little q. That would be a lot easier. We already did that problem in the quiz, but we don't have that. We have a 2-dimensional problem, but the idea is still the same. For each charge, think about the electric field that it has at the location of the test charge, draw it, calculate it, and then use components. So E1, the field that Q1 will exert at the origin, so positive charge will push this positive away, and that's going to be field E1. How do we calculate it? Well, we know Q1, we know K. Now all we need is R1. How far away is it? So that's R1. Okay, E2. Same thing, K Q2 over R2 squared, and it'll point towards Q2. Pretend like I'm pointing at it. And this would be R2 and E2. And finally, E3 would be going towards that negative charge, so that would be R3. Okay? And we calculate E3 is K Q3 over R3 squared. Okay? And at this point, once you have all of these guys, well, now it's time to set up a table. Okay? So here's your table. Maybe I'm being too neat. Is that a thing? I don't know. Okay. And so these are going to be the x and y components of E1, E2, and E3. But before we can go on any further, we need to know the angles. Okay? So for example, for E1, in order to split it into x and y components, we need angle theta 1. And that's the same as this angle right here. And if we know the x and y components of this point, I think it's negative 0.15, negative 0.2. I could be wrong on my numbers. I don't have my book with me. And so what you would do is you'd find theta 1 would be the inverse tangent of 0.20 over 0.15, y over x. Okay? And that's the same as this theta 1 right here. And so that means that Ex would be E1 cosine of theta 1, and it's in the positive direction, but Ey would be negative E1 sine of theta 1. Okay? Now I'm not going to do the numbers, and you get the idea. These are very similar, and then what you should do is find E totes, add them up, and then that's going to give you a new vector with Ex total and Ey total, and then you just need to do the math. So having all of this is not going to be sufficient when you turn it in Monday. You're going to have to carry it out and get the final answer. Okay? So that's an overview of 57. Now, I think we have time, so let's quickly talk about 47. And 47 said, okay, we have a positive charge surrounded by a conducting shell. Okay, that's close enough, you get the idea. This is a conducting shell. And we want to know basically what is going on with the electric field here. And this is a charge of positive Q. Okay, now because it's conducting, it's metal, the electrons are going to be drawn to the inner surface so that there will be some negatives, which when you add them up, will add up to negative Q. Now those negatives had to come from somewhere, so that means that the outside will become positive Q. Okay, so outside is positive Q. Now this does a couple things. Actually, I'm going to try to redraw that guy. Okay. Now, one thing that this does, that's better, is it separates the charge on the conducting shell. There's negative Q on the inside, positive Q on the outside, and if I were to draw the electric field, my electric field is going to go from positive to negative, so kind of like this. Okay? Well, what about for the electric field inside of the conductor? Well, we know the answer to that. The electric field inside the conductor should be 0. Now, one more way to see this is to put an imaginary dotted line inside of this. And if you remember what we talked about with shielding, we said that this electric field depends on the total charge inside of that circle. And if I look at that, well, it looks like plus Q and minus Q, plus Q from this guy in the center, minus Q from all the guys on the outside, and it looks like the total charge I have going out to this green circle is 0. And I'm not counting the positive on the outside. I'm just starting in the middle and going to the green circle. And because of that, if I have Q equals 0, then my electric field is going to be 0. Okay, but then once we get outside of the conductor, then it starts going out again. And one last thing that you might want to pay attention to is that if I zoom all the way out, okay, what this looks like is basically a tiny positive charge, okay, with a little thing surrounding it, but basically field lines coming out. So if you zoom out enough, it just looks like a positive charge. The conducting shell really doesn't have anything to do with it. Okay, and then finally, what would happen if the charge was reversed? So if I had a negative charge surrounded by a shell, well, it would be the exact opposite. All the field lines would point inwards, and I would have pluses on the inside and negatives on the outside. I'm not drawing the whole thing, but you get the idea. Okay, so hopefully this helps, and in the next video I'm going to give a short lecture on electric potential energy.